So before the break, we were looking at the area and perimeter of shapes, two-dimensional shapes, and now we're going to move into three-dimensional shapes and look at the volume of prisms and cylinders, and then later on some circles or some spheres and some cones. Now, because you're probably noticing it, you'll see that I've erased the note. It was because I filmed this in portrait mode versus landscape mode, and so everything was sideways, so I had to redo it. So this is my second take on it. Hopefully we get through this one properly, and then we'll be good from here. So some definitions: volume and capacity. We want to differentiate between these two because we'll use these two terms, and they mean they're often used interchangeably, but technically they mean something different. The volume is the measure of the space an object occupies. So how much space does it take up? When an example might be if I have a bathtub full of water and I drop a cylinder into it, how much water spills over the side? That amount of water, that's how much space that's taking up. Where capacity is how much would fit inside. So say I had the empty bathtub, the capacity is how much water will actually fit inside the bathtub. So it's a measure of how much something can hold. So when you look at volume, you're finding out how much actual room it takes up, and then capacity, you're looking at how much will actually go inside the object. Now, there's a couple little definitions here. So we're looking at prisms today in this video, and a prism is a three-dimensional object whose ends are the same. So in the case of something like a rectangular prism, I'm going to have a rectangle as my face, and then if I extend these back, and this is looks something like that. There's a rectangular prism. I have my rectangle, my say length and width of it there, and then I can have, depending on where the object is, you might call it depth or you might call it height. Some people call it height, so length, width, and height. So the volume of a rectangular prism, both ends are the same, or you could even say that these ends are the same. All the ends are the same in this one, but it's length times width times height, or LWH. And yes, I do write this one in cursive all the time. I don't know why, it just is the way I've always written it, while the other ones I don't. Now, in a case of a triangular prism, we're going to take our prism shape by taking a triangle base and extending that back. So if I have a little triangle here, that's my base shape. So it has a base and a height in here. And then we can extend that back. And now, because we use the terms base and height for a triangle, then we'll often use the term depth, or D. So we'll call that the depth of the triangle. It's the same idea as being the height here. This could be the depth. It's just the third dimension of the triangle. So the area is 1/2 times the base times the height of the triangle times the depth of the object, or V equals 1/2 base height D, like that. So we have the area formula times that extra dimension. So all we're doing going from volume or from area to volume is we're actually just adding an extra dimension onto our shapes when we're working with prisms anyways. So if I have a circle, with a radius r. Then to make it into a cylinder, and a cylinder is a circular prism. We just call it a cylinder because its circles are special. We just add a height to it, and so our volume would be the pi times the radius squared, just like a circle. There's the area of a circle times that height, or volume equals pi r squared h. Okay, so there's our three formulas. You always have access to these whenever you need them, so you don't have to memorize them, but good to be familiar with them. The more you can get them stuck in your head, the easier it'll be to do your work. So in general, whenever we're working with a prism, the volume of that prism is the area of the base multiplied by the height. And that's what we have here, the area times the height, the area times the height, the area times the height. Or in this case, the depth. So when we're working with volume, now we're using cubed units. In our case, we're going to be using the base unit of meters for our volumes because we're working with the metric in many cases. But it works the same if it's feet. It would be cubed feet, cubed yards, cubed inches. Whatever units you're using, we're going to cube them in the case of volume. So in general, you'd have your meters cubed, your centimeters cubed, millimeters cubed, and kilometers cubed. Those are going to be the four main ones that we see. In the case of capacity, so volume, again, the measure of the space something occupies, so we can measure the outside of it with our ruler and figure it out. The capacity is how much will fit inside, so we generally are thinking of a liquid type of volume, and so that's what we call capacity. So capacity, how much milk fits in this carton would be an example. And so in that case, we're going to use liters and milliliters most commonly. You ever see any European products in that for kitchen products, or you go to IKEA, oftentimes you'll actually see things listed as CL, centiliters. So just like centimeters, there is a centiliter. We just don't use it very much in North America, but centiliters is another possibility there. So just a quick reference, if you start with your base unit of meters or liters, okay, so that's a value of 1. If I need to look at kilometers, then there's 1,000 kilometers, or sorry, 1,000 meters in a kilometer. In the centi, and I'll just use centimeters because that's our most common one here. There's 100 of those. And there, I shouldn't put the equal sign. And then in millimeters or milliliters, there is 1,000. So these, to convert from our base unit of meters to any of these, so if I have centimeters and I want to go to meters, I have 100 centimeters in a meter, so I divide centimeters to get to meters. So if I want to go from milliliters to meters, I divide by 1,000. So if I want to go this way, I'm going to divide. And I should stop that at the meters. Went a little too far. So stop that at the meters to right here. If I want to go from kilometers to meters, then I'm going to multiply it by 1,000. And if I want to go the other way, I'm going to divide And to go down this way, I'm going to multiply. So if I had 100 milliliters, I would do 100 divided by 1,000 to get the number of liters. If I had 2 liters and I wanted to get milliliters, I would take my 2 and multiply it by 1,000 to get 2,000 milliliters. So you can use that as a little reference kind of guide there. If you don't remember them, you should be fairly familiar with them by now, hopefully. We're not going to do a lot of conversion, but occasionally it comes up. And then the last bit here is that the rate of volume to capacity. So if you have 1 liter, that is 1,000 cubic centimeters, or 1 cubic meter. So sorry, that is incorrect. Let's fix that. Scratch that last part there. 1,000 liters equals 1 cubic meter. That's a little bit better. So that last part was incorrect. That was my fault. I was rushing through this, I think. 1 liter is 1,000 cubic centimeters, or 1,000 liters is 1 cubic meter. Okay, so keep that in mind when you're calculating these out, because we're going to be doing some conversions. You can refer back to this. So if I flip the page, now we have just some simple calculations with them. So for each figure, we're going to determine the volume and the capacity. So I have a rectangular prism. In the first one here, the volume of a rectangular prism is length times width times height. So I have a length and width of 5 by 12 on my base here, and then a height of 15. So I just multiply all those out. 5 times 12 times 15 is going to get me 900 cubic centimeters. And then if I want to calculate the capacity, well, we have a ratio there that there is 1,000 cubic centimeters. Flipping that back over quick. 1,000 cubic centimeters equals 1 liter. So I have 900 cubic centimeters. I'm going to do 900 centimeters cubed divided by 1,000. And, sorry, there we go. And when we do that, 900 divided by 1,000 is going to give me 0.9 liters. So 900 cubic centimeters, 0.9 liters. If we look at the next one here, we got a triangular prism. You'll see these sometimes in science class. We use these to refract light, I believe it is, and bend the light, break it up into that little rainbow that you might see on the cover of the Pink Floyd album there, or on millions of t-shirts. The volume of the triangular base prism is 1/2 base times height times depth. So our volume here equals 1/2 times our base of 6, our height of 4 there, 6 and 4, and our depth of 15. And again, when we're working with a number like a half or a fraction in these, you can either convert it to a decimal. So 1/2 is 1 divided by 2, or 0.5. Or you could just type this in your calculator as 1 divided by 2 times 6 times 4 times 15. In any case, you should work out to a result of 180 meters cubed. Now, we got to calculate the capacity of that. So 180 meters cubed times, now there is 1,000 liters in a meter cubed, so we need 1,000 times this. And this is going to equal 180,000 liters. So this pyramid, or this triangular prism here, has 180,000 liters of capacity. And in the next one here, we have a cylinder, so volume equals pi r squared h. Volume then is 3.14 we can use for pi times r squared, which is 6 squared, times the height, which is 7. And then we can multiply all that out and get approximately 790 meters cubed. Remember, we're doing 6 squared, so that is 6 times 6. It is not 6 times 2. 6 times 6 is 36. Why'd I use a 6 there? Because what is our value here is given is a 12 as the diameter, and we want the radius. Remember, the radius is half of the diameter, so only 6. The next part is our capacity. So we have 790 meters cubed. And again, there's 1,000 liters in a meter cubed. So 1,000 times that is going to get me 790,000 liters. So some pretty big numbers there. Now, in the worksheet that I shared there, the question sheet that I shared, you're going to take a look at these numbers here. Numbers 1AB, 2AB, 3AB, 4, and number 5.